Section 5.1, page 4. So example 5 asks us to use 4 rectangles and left endpoints to approximate the area under the curve f of x equals x to the 2/3 power plus 2 on the interval from 0 to 8. So we were originally given this graph without all the drawings, where we could see that the graph went from 0 to 8 and our function f of x was given to us. So I'm asked to find 4 rectangles. That means n is 4. I need 1, 2, 3, 4 rectangles. And specifically, I'm going to be using left endpoints. But let's go ahead and start by determining where those rectangles end, because you'll notice it's not 1, 2, 3, 4. So for the width, which we refer to as delta x, we have this formula: where does your interval end minus where does your interval start, divided by n, the number of rectangles you want. Well, our interval ended at 8, it started at 0, and we want 4 rectangles. So what this is telling us is we have a width of 2 for each rectangle. So if we start at 0 and we add 2 and continue to add 2, we're going to eventually make it all the way through our range, and we're going to have 1, 2, 3, 4 rectangles. So I highlighted 0, 2, 4, 6, and 8, the edges of my rectangles. Now I didn't know the height of my rectangles, so at first I just focused on the columns. I knew my graph went between 0 and 2, not 1, for my first rectangle. Now I'm ready to find the left side by putting a dot on the left side. So I focused on this rectangle. I looked at where did the graph cross, and the left side happened to be lower, and so I went across to the next column. Now going from 2 to 4, I looked at where does the graph cross on the left side and went across. Left side and across, left side and across, until I hit that wall of 8 where our range ended. But remember, I'm doing all of this to approximate the area, because we know rectangles, unless you go to infinity and take the limit, is not going to be as exact as possible. So for an L4, 4 left end rectangles under this curve, I need to take the height of the first rectangle times its width. Well, we've already decided that the width is 2 every time, which actually we can just factor out. But the height, instead of looking at the graph, I'm actually going to use the function. When I took my first column, it was the left side when x was 0 that determined the height. So I'm going to take x is 0, plug it into my function so that I have 0 to the 2/3 plus 2, which is really just 2. Now my next rectangle started at F2. That determined the height. So I'm going to come to x to the 2/3, although x is 2, plus 2. And this is going to give me a long decimal answer that I went ahead and rounded to 4 digits. You should be instructed what to do for each problem. Again, plugged 4 into the function, simplified, plugged 6 into the function and simplified. There's a note here that I didn't plug 8, right? I used just the first 4 digits because when x is 8, I don't have another left end rectangle. 8 is actually the right end of my last rectangle, and we don't use it. So combining all of the heights into a single sum, multiplying by the width, and basically the area under this curve from 0 to 8 is approximately 30.82, whatever units we're measuring. Here's another example. Number 6. Suppose the odometer, the gauge that determines distance, on your car is broken, and you want to estimate the distance driven over a 60-second time interval. So we're going to take the speedometer, not a gauge that's broken, but one that tells you how fast you're driving, and we're going to read it every 10 seconds. So we're going to probably have a computer doing that, but basically We're looking at a 60-second time interval. So our interval starts with no seconds and ends 60 seconds later. So we first look down and the car says we're going 30 miles per hour. 10 seconds later, 35 miles per hour. 20 seconds later, 43 miles per hour, or whatever range, or it says feet per second, so it's not miles per hour, it's feet per second. So we want to estimate the distance traveled. Our odometer is broken and it won't tell us that, but we can estimate it for this particular time period for the velocities at the beginning of each time interval. That's going to be important. So doing what we did above, we need to figure out what is the distance of all of our rectangles, or was the area of all of our rectangles to give us the distance, right? We need to sum up the length and the width. So because it says beginning endpoints, these are these left endpoints. True, 0 could have been over here in the corner, but for clarity, I wanted you to see that I took 0 to 10 seconds and then, 10 to 20 seconds. So we knew right at 0 seconds, we noticed the car was going 30 miles per hour. And then at 10 seconds, we were going 35 miles per hour. So when I chopped up into 10-second intervals, I then started with the speed on the left and just kind of drew that across to create all of these different rectangles. So instead of having to plug into a function, we know that our width is 10 for all of these, etc. And the speed, the velocity at each time increment is given to us in a table instead of us having to mathematically calculate it. So we're really going to go ahead and factor that 10 out. I put it on the right side instead of the left side like I've been doing. And we need to add 30, 35, 43, 45, etc. until we add the last digit. 238 feet per second combined and multiplied by 10. So because this is in feet per second, we traveled 2,380 total feet in 1 minute, which is 60 seconds.